So today we're going to discuss the first set of problems for presentation 1 about the beam and column deflection. So our team consists of myself, Subian Iluzani, Charles Bemo, and Abdullah Lanzi. Next. So our structure has a vertical load applied with properties of, for the vertical member, it has a length of 14 feet, moment of inertia of 275 inch to the 4. The cross section is 1,000 inch square. The modulus of elasticity 18,000 ksi, and eccentricity for 9 inch for the rest of the problem. For the horizontal member, the length is 9 inch. The moment of inertia is 10,000 inch to the 4. Cross section is 1,000 inch square, and the modulus of elasticity of 1 million ksi. So the first problem, it's consists of looking to compute the exact solution for the maximum deflection and maximum moment using the following equations, since the structure has a nonlinear deformation. So the first problem was like straightforward. We had to plug in the data that's shown in the left table to Excel, and using the previous formulas in the previous slide, we were able to find the maximum deflection and the maximum moment with the exact solution, of course, using different loads of 50 kips, 125, 200 kips, and 275 kips.
Good afternoon, Dr. Austin. So for part 2 of our problem, we had to employ the virtual work method to do a second order elastic analysis to find 3 iterations of the maximum deflection and the maximum moment beam. So to start, for the first iteration, we simply use the formulas from structural analysis and other classes that we've used before. Now, since this beam has an eccentricity on each side, instead of treating it as a point load, like the problem shows, we treat it as an equal and opposite moment on each end of the beam. So that is why our maximum deflection formula is going to be moment times length squared divided by 8EI, and the deflection at a given distance, the moment at that distance times length minus x divided by 2EI. And the moment for the first iteration, the formula is not pictured here, but it's simply force times distance. So P times the eccentricity plus the distance of the deflection, the distance times the deflection. So for the second iteration, that is when we start employing virtual work, and we use this last formula here. Q times delta max. Q is just the 1 kip virtual load. Delta max is what we're trying to find. And then the right-hand side of the equation is summation of areas times moment at the application of the virtual load. So for the second iteration, we have to find the areas. It's divided into 4 areas, but it's a mirror image over the center point. So really, we only have to do calculations for 2 areas. Now, these areas are both going to be trapezoids, since we already have that moment right off the bat on each end. So we calculate the area, we calculate the centroid, just using the proper formulas for a trapezoid. And then we find the moment at the application of the virtual load, one at the quarter point and one at the halfway point. And then we use those and we find a new deflection and a new moment at two different points. And then with those new moment values that we have, we do the whole thing one more time. And each time we improve our accuracy by a small amount. So these are the results that we came up with. As you can see, the maximum moment is not significantly higher than for example, with the 50 kip load, we had a 450 moment at each end already. So that's an indicator that our relative error is going to be very low because these numbers are close to begin with. So problem 3 was just asking for the relative error that we calculated for problem 2 versus the exact solution. So the way we came up with this was the exact solution from part 1 minus the maximum moment from the third iteration in part 2 divided by the exact solution maximum moment and multiplied by 100 to give you a value in percentage. As you can see, the 50 kip load, the relative error was about 0.1%, so extremely low. And then it does increase exponentially as we get up to the 275 kip load, and our error is just over 3% there. So still very low error considering we only did 3 iterations. You normally have to do maybe a dozen to get error that good.
The following steps were performed for solution to this problem. First, defining nodes. The nodes are defined using geometry defined nodes. Then, the coordinate of the nodes are inputted accordingly to get the node at important location, the edge of the beam column. Second, defining elements. The elements are defined using geometry defined elements. Then two nodes are selected where an element or member is desired and apply is pressed. Third, defining and assigning section. The section of an element are first defined using properties, define section after inputting necessary section details, area, moment of inertia, and others. Then it's named and saved. After defining a section, it is assigned using properties, assign section by selecting the element and choosing section name and pressing apply. Fourth, defining and attaching material. The material are defined first by using properties, define material. After inputting the necessary materials details, Young models, Poisson ratio. After defining materials, then the material are attached to the section by selection element and pressing apply. The eccentric link were modeled with a different section and material. The fifth, define end restraint and load. The support to the beam column are assigned by using condition fixities. The nodes in the beam column is selected and the desired degree of freedom for the nodes are restrained. Load are defined in the manner the nodes are selected and required load is assigned. Sixth, performing second order analysis. Then second order elastic analysis is selected in analysis and in the increment size of analysis is 0.2 with the program determined number of increments equal 15. A planar frame was selected and apply was pressed, which led to the analysis of beam. The result for the moment and displacement were checked to each load application 50, 125, etc. using result tabs. And the related results are summarized in a table on next page. Here it's seen as loads are increased, both deflection and the moment are increasing, with the highest deflection is for 275 kips. Next, please. The results show very accurate results with different less than 101%, which shows the quality of modeling and the power of Mustang to compute results with much accuracy and consuming less resources and time. Next. Thank you.
Thank you, Doctor. We'll be waiting for your valuable feedbacks. Thank you.